Something in the universe is acting like anti-gravity, and it's winning. Not just over planets or galaxies, but over everything. Right now, as you sit here, the space between galaxy clusters is being stretched so fast that distant galaxies are slipping away from us faster than the speed of light. Not because they're moving through space, but because space itself is expanding underneath them. And the terrifying part is, this acceleration is getting stronger with time. Whatever is driving it already makes up about 70% of the entire cosmos. We call it dark energy, mostly because we have no idea what it actually is. To understand dark energy, you first need to know that the universe is not static. In the 1920s, Edwin Hubble measured the light from distant galaxies and found it was redshifted, stretched to longer, redder wavelengths. The farther away a galaxy was, the more its light was stretched. The simplest explanation: space itself is expanding, carrying galaxies apart like dots on an inflating balloon. For decades, cosmologists expected this expansion to slow down. Gravity is attractive. Every galaxy, every cluster, every cloud of dark matter should be pulling on every other, gradually breaking the expansion. The big question was, would gravity be strong enough to eventually stop the expansion and reverse it into a big crunch, or would the universe expand forever, just more and more slowly? The answer arrived in the late 1990s from something as dramatic as a cosmic explosion. Two independent teams studied Typler supernovae, white dwarf stars that detonate with almost identical brightness. Because their true luminosity is known, they act as standard candles. By comparing how bright they appear to how bright they should be, you can measure their distance across billions of light years. When astronomers compared those distances to the redshift of the host galaxies, they expected to see signs of a slowing universe. Instead, the supernovae were dimmer than predicted. They were farther away than they should have been if the expansion were decelerating. The only consistent explanation: for the last several billion years, cosmic expansion has been speeding up. Something is pushing, not pulling, on the fabric of the universe. So what is dark energy, physically? The simplest idea is called the cosmological constant, usually written as the Greek letter lambda. In Einstein's equations of general relativity, lambda acts like a built-in energy density of empty space itself, vacuum energy. Even when you remove all particles, all radiation, all fields, the nothing that remains still has energy. And that energy has a very weird property: it gravitates repulsively. In general relativity, energy and pressure tell space-time how to curve. Ordinary matter has positive energy and positive pressure, which leads to attractive gravity. But vacuum energy has positive energy and negative pressure. On cosmic scales, that negative pressure dominates, causing space to expand faster. If dark energy really is just a cosmological constant, its density stays roughly the same as the universe grows, so its influence becomes more and more important as matter thins out. Dark energy isn't just a clever fit to supernova data, it leaves fingerprints all over the cosmos. One is in the cosmic microwave background, the afterglow of the Big Bang now cooled to just 2.7 Kelvin. Tiny temperature ripples in this radiation, mapped by satellites like WMAP and Planck, encode the geometry and contents of the early universe. The pattern of hot and cold spots tells us space on large scales is very close to flat, but the amount of matter we see, both normal and dark, is only about 30% of what's needed for flatness. The missing 70% behaves exactly like a cosmological constant. Another clue comes from the large-scale structure of the universe, the cosmic web of galaxies and clusters. Gravity tries to pull matter together into denser clumps, while dark energy pushes space apart, diluting those clumps. By measuring how structures have grown over billions of years, using galaxy surveys and gravitational lensing, where massive clusters bend the light of more distant galaxies, we can see dark energy's tug-of-war with gravity in action. The data all point to the same strange conclusion: an accelerating universe dominated by something very smooth, very diffuse, and very repulsive. If dark energy is real, it completely reshapes the universe's future. In a cosmos with only matter, distant galaxies would always remain, just getting farther away more slowly. In our dark energy-dominated universe, the opposite happens. As expansion accelerates, more and more galaxies cross a kind of cosmic event horizon. Beyond a certain distance, space between us and them expands so fast that their light will never reach us, no matter how long we wait. Fast forward tens of billions of years. To observers in the far future, almost all galaxies outside their local group will have vanished from view, redshifted into oblivion. The universe will look emptier, colder, and more isolated. If dark energy is a true cosmological constant, this acceleration will continue forever, approaching a state called heat death, where energy is so evenly spread out that no large-scale structures can change or do work. It's a very slow apocalypse, written not in fire, but in exponential expansion. But what if dark energy isn't constant? Some theories propose quintessence, a new, slowly evolving field permeating space similar to the Higgs field, but with different dynamics. In these models, the density of dark energy can change over time, slightly altering the expansion history. Observationally, we describe dark energy using an equation of state parameter, W, which relates its pressure to its energy density. A pure cosmological constant has one exactly equal to -1. Quintessence predicts W that can differ from -1 or even vary with redshift. There are even more extreme possibilities. If W is less than -1, a scenario nicknamed phantom energy, the acceleration grows so violently that, in the far future, it could tear apart galaxy clusters, then galaxies, then solar systems, and eventually even atoms in a big rip. On the other side, if dark energy decays or changes sign, cosmic acceleration could slow, stop, or reverse, leading to a very different fate. Right now, our best measurements put W very close to -1, but with uncertainties that still leave room for surprises. So what are the big open questions? At the deepest level, is dark energy a new ingredient in the universe, or a sign that our theory of gravity is incomplete on cosmic scales? Maybe general relativity, which works beautifully in the solar system and around black holes, needs modification across billions of light years. Competing ideas like modified gravity or extra dimensions try to explain acceleration without invoking a mysterious energy component, but so far, none fit the data as cleanly as a cosmological constant.